Good afternoon, everyone. So today we will be looking into the mass transfer limited impedance. Okay. So this is class 11. So how we will have the mass transfer limitations affecting the mechanistic modeling. That is what we're going to deal in today's class. So if we just look into what we saw in class 10. Yeah. So in class 10, we looked into Franken-Isenberg model, where we say that the absorption of species is related to the previously absorbed species. So the new species have the tendency to get absorbed to those species which were previously absorbed. So that means kind of some sites were having higher affinity. So there, to count for that interaction between the absorbed species, we account for that interaction in the rate constant in terms of a term exponential raised to beta g theta. So when there is interaction happening or when one adsorbed intermediate gets adsorbed closer to another adsorbed intermediate, there can be repulsion. So in that case, we assign beta to be a negative value. So when the potential increases, the fraction of sites adsorbed initially increases, and then if we are adsorbing more species, it will get adsorbed by the previously adsorbed species, and the repulsion happens. So that means when all potential keeps on increasing, species adsorption increases, and after one point K1, that step which corresponds to the mode formation of that adsorbed intermediate species reduces. Because for that step, we say B1 beta 1 is negative. Then the same approach, except that this one in the derivation will have an additional term in terms of g theta beta. That relation will be there, and once you solve it, you will get the expression. Okay. Then we looked into assignment number 7, where we looked into how many absorbed intermediates will be there, etc. Those kind of questions. How many DC potentials are required to model the mechanism, etc. To model the impedance data, etc. Then we came to the diffusion effect. So sometimes the rate of the reaction will be very fast, but at the same rate, the molecules might not be available, and there will be the less number of molecules will be available at the interface. So there is a gradient in the available concentration across the electrolyte interface, and there the diffusion effect comes to play. And if we say that the electrolyte interface, there is a small thickness delta where this concentration gradient is present. So we can go for rotation where convection effects come to play, the mixing happens, and the reactant molecules are easily available, and the reactant products can easily get out of the surface. So mass transfer to an exit can be reduced. So we can use RD, rotating disk electrode, in order to induce this rotation or mixing. So boundary layer thickness can be described using the levich equation, where it is related to diffusion, the rotation speed, and to the viscosity. And so if I'm increasing the rotation speed, it will cause a decline in the boundary layer. It is inversely related to square root of rotation speed. Okay. Then for actual surface, the total current for any electrode reaction is happening will be sum of the current due to kinetics and due to the mass transfer. And yes, what we saw when we are applying potential, there is a consumption of the reactant, product formation occurs, diffusion of species. So this involves a flux or the fixed law of diffusion also, which says dou C by dou T is equal to dA dou square CA by dou X square. There is product which becomes dou CB by dou T equal to dB into dou square CB by dou X square. So in steady state, we can say that the change in concentration with respect to time is zero. Okay, so the first thing we saw, how is the kinetics and mass transfer limited Plus, when my mass transfer comes to play, how is the impedance plot changing? So when the kinetics is there, when the potential keeps on increasing, what happens? The resistance to charge transfer reduces, right? Because the species are coming, speed when the potential is increasing, speed of the reaction is kind of enhanced, reactance comes, products release, etc. But when there is mass transfer coming to play, when you're increasing the potential, reactants might not be easily available or the products can clog the surface, so the reaction speed reduces. So because of that, when mass transfer comes to play, we say that in the impedance, the charge transfer resistance is actually increasing. So then we saw when with the rotation, how will it change? This is the figure. So speed of rotation also has an effect over the time. It forms a line which is 45 degree, which is called the warburg. And for we all can get finite and the semi-infinite warburg condition. Semi-infinite means you will have to go to very, very low frequencies where you will see that it is not, it will meet the x-axis but at a very, very low frequency. So when kinetics is there, you will have only the what is Faraday reaction. But when you have that in series with the Warburg, you say it is kinetics plus mass transfer. So we saw how we are writing the current and all. Equilibrium, you will say that the forward and backward reactions are equal. This is similar or the case is same as that which we saw for recited, except that diffusion is coming to play. So we here the thing is that the electrolyte interface, we cannot say that the Ca and Cb are equal to the bulk concentration. They're different. So we have to find out what is the concentration of the species at the interface and then progress. For that we are using Fick's law. We already told it's steady state and then we derive, we substitute, we find the water Ca at the surface and Cb at the surface. Then we find out the net rate of consumption of the reactant species and all. We substitute, we find it out, rearrange, find out the current. Okay. So the next thing we'll be moving on is to unsteady state condition and the semi-infinite condition. So this is summary of what we had looked in the last class. So I'll wait for a couple of minutes to see if someone is joining the class and then progress with unsteady state condition and semi-infinite condition. So we'll be starting at sharply after that. Okay. we'll start with the derivation and then move on with problems. Okay. So unsteady state means also concentration not just changes over the position but also with the time. So just giving a brief idea, like so what are the basic question we are using? So when small amplitude sinusoidal perturbation is applied, so we can obtain the current by solving the following formulas. Okay. The first one is dou Ca by dou T equal to dou square Ca by dou x square into Di. So there's a fixed law, and then you have the current NF K10 exponential V1E concentration at zero position and at a fixed time minus K10 exponential V minus 1F CB at concentration 0 at that interface and any time T. Now we'll also have to use the expression for rate constant, which is given by Ki equal to Ki dc 1 plus Bi EAC. So we have to also understand what happens to the PDP curve, which is the current versus potential when the rotation speed increases, when potential increases, etc. So let us consider the PDP curve. We'll write in the next page. So PDP curve of a simple electron transfer reaction, which we are looking into now. Now what will happen if we are changing the rotation speed? Or I can say a different boundary layer thickness, which is like when I am increasing the speed, boundary layer thickness will reduce. This is case number one. So, so what is actually happening? Initially, you will have a kinetic regime where potential and current has a what to say linear regime, and then it becomes non-linear, and finally the current saturates. So no matter how much ever potential you are increasing, the current wouldn't change. It is kind of saturating. Same thing will happen if you are going to the negative potential also. Okay. So let me say this is at some what to say 200 micrometer thickness. So now I'm gonna reduce the thickness of the boundary layer. So when boundary layer thickness reduces, what is happening? So the region in which the region in which you see a concentration gradient is reducing. So molecules at less are slightly in better position to migrate towards the electron-electron interface. So the mass transfer effects are slightly reducing. So obviously the current you get with that potential is going to increase. That's the first thing. And when does the mass transfer come? When there is a concentration gradient. So the thickness reduces, the concentration gradient you're gonna see, its effect is gonna be reduced. Or that means molecules can come little easily than the previous case. Previous case means the one which is shown in the red. So what does that mean? That also means, so as I told, the current is gonna increase with the potential. It is in a where current is little higher when compared to this case, when the boundary thickness is reducing. The next thing I said is mass transfer limitation has reduced. So the region in which you see what to say increase in the current, is for the potential to be linear is increasing. The sense you see this region. Here you see at up to this region. Up to this region, you see here, this much region is current was potential kinetic regime. And comes here, it is only this much. I'll again draw. Uh, uh, the next one. So what I meant is the first case or the second case up to this region, it is having a kinetic regime or a linear relationship, current and potential. But when I'm reducing the, when I'm increasing the, okay, let me write that also. Now this is the case with 100 micron. So from 200, it's becoming 100. So now when I'm reducing the, when I'm increasing the boundary layer thickness, first then current will reduce, and this linear regime stops here. On the contrary, here it is up to this much. So the linear regime you see also is increasing when you are increasing the, when you are decreasing the boundary layer thickness. Now let me take the last case where I, okay, in that case also, here also you will see the same thing. Here it was still this. Now the next case is, if I say, so here it was still this, now it is still this much. This is 10 micron. Same way here also. So two things happen when boundary layer thickness reduces. You will see that the current increases with potential. That is the first thing you see. And the next one will be that the linear regime, potential versus current increases. So these are the two things you observe when your boundary layer thickness is reducing. So this was current milliamp per centimeter square, and this is the DC potential versus OCP. I'm talking about different over potential. Okay. Now the next thing is surface concentration as a function of DC potential. So when same thing, you have EDC versus OC3, and you have concentration. So this is zero. Okay, this is positive, this is negative, this is positive side. So when I'm increasing, okay, okay. Now I'm saying when I'm increasing the over potential, the rate of the reaction is increasing. So rate is increasing because A that is formed is getting consumed. So over the time you'll see that the A gets consumed. Finally, the rate that this is getting consumed is reducing. Why reducing? Because mass transfer is playing a role, and after some time the materials are not readily available. So the rate at which it's consumed is reduced or the concentration reduces. Same way when you go to the negative potential, so this is concentration of the reactor. When I'm going negative, this reactant concentration increases, and after some time, it kind of what is saying becomes stabilized kind. It doesn't increase in the same way. Now, on the contrary, when it is concentration of the product at positive potential keeps on forming, and then it kind of stabilizes. Here also, in negative, it reduces and it kind of. So, when the potential increase over a period or over a particular value, the concentration of the reactant in the product, they cannot meet that level, or concentration of reactant cannot meet that level, and that's why it is reducing or it is kind of stabilizing. Same with the product formation also. get stabilized, not stabilized, I can say, it wouldn't change rapidly. Okay, can decrease or increase, but it's not rapid increase or decrease, unlike the initial phase that you see. Okay, so if I'm applying a potential, the concentration will be changing with respect to time and also with respect to the position or the space. So concentration is depending upon two factors. One is not only x, which is the change in the position, but also on the time. So if potential is changing very fast, the diffusion cannot keep up the limit of the concentration of the reactant. So let's move on to the unsteady state. So same reaction, A given B plus electron, you have K1 and K minus 1. You have potential to be sum of EDC plus EAC, and you have the rate of, so the reaction current density to be NF into rate of reaction. You have N equal to 1, F into rate of reaction. For our reactions K1, CA at x equal to 0 minus K minus 1, CB at x equal to 0. Now we know that K1 equal to K1 DC into 1 plus B1 EAC. K minus 1 equal to K minus 1 DC 1 plus B minus 1 AC. So here you have three independent variables. Which are they? One is EDC or E. You have concentration of the reactant, concentration of the product. These are the independent variables. So presently we are looking at a finite boundary layer thickness problem. So you have IF equal to IFDC plus IFAC. What is IFAC? It's basically that from the electric current, right? So with that I can write it as the change from the DC current, right? And now I can also express this as dou IF by dou E, which is the first variable, keeping the concentration of CA and CB constant. I already told there are three independent variables, E, CA, and CB. So likewise, I can differentiate it with respect to all the variables. So this becomes equation number 1. This is important. Now, we already told IF equal to K1 CA minus K minus 1 CB into Faraday's constant. Now let's write K1 as K1 DC into 1 plus B1 EAC CA at x equal to 0, and I'm saying it's steady state for time being. So and K minus 1 DC 1 plus B minus 1 EAC CB at x equal to 0 steady state. Now what I'm going to do is, I told there are three independent variables E, CA and CB. I want to differentiate VIF with respect to potential, concentration of the reactant, concentration of the product, these three variables, and see what the values are. So the first one is VIF by VE, keeping concentration of the reactant and product constant. So what do I get? This is the full equation. I'm differentiating it with respect to CA and CB. I'll get K1 into B1 CA minus K minus 1 into CB into 1 plus B minus 1, that term, right? So I'm going to write that we have written this. Okay. Now the next equation is the differentiation of IA with respect to the concentration of reactant and product. So I'm differentiating it. Only the first term will come K1 DC into 1 plus B1 EAC. So EAC is already constant, so that term will stay. Okay, I didn't change the notes, I'll do that. Now same way, do IF by do CB and E and CB, this becomes minus F K minus 1 DC. Now what you have to do is you have to determine delta CA and delta CB. So delta CA equal to CA. Same like how we have expressed IF, this will also be like in terms of AC. So I can, same like that, I can write CA AC not C not at AC. That is what it means. Exponential j omega t plus phi a. Now CA C naught it becomes a function of gamma and omega, which is proportional to EAC naught. Okay, same way phi a, that's also function of the chi and gamma. It's independent of EAC naught as long as EAC naught values are small. So it is with that conditions when we are writing, we need C naught and x equal to 0. So how do we write that? dCA by dou t equal to dA dou square CA by dou x square. And you have CA equal to CA DC plus CA AC portion and CA DC I can write as such. And because of the AC, if I write, can be written as del CA. Now you can substitute for CA DC plus CA naught exponential J. The same thing we got from here. Similarly, CB becomes CBDC plus CBAC equal to CBDC plus del CB. And I can again write the same as that I've written for CA. Now the same thing I'm going to substitute in the fixed law of equation. So how do you do that? Dou CA by dou T equal to dA del square CA by dou x square. So what will I get if I substitute this above equation, this one and this one in the fixed law of equation? That's what we're going to see now. It becomes dou by dou T CADC plus CAAC equal to dA dou square by dou x square of CADC plus CAAC. So we know that CADC is a constant value. Like it is dependent on the DC potential, it's a constant. The other one CAAC is sinusoidal. So CADC, when we are differentiating it with respect to time or with respect to the position, it wouldn't make an effect. So how do we write that? Wouldn't make a difference means it's a constant and it will become equal to 0. Now, this we have already written that CAC can be expressed sinusoidally, and this is how the formula will come. So this from the sinusoidal we have written writing it in the polar way, polar coordinate form. Okay. Then if I write CAC equal to CAC naught e raised to j omega t e raised to j phi a. Okay. The constants can be taken together, and this becomes C8 e raised to j omega t. This part which I'm going to substitute back in this equation. It becomes important because we're going to differentiate it with respect to time. So that's why we are writing it in terms of the polar coordinate. Here we have written in terms of polar coordinate because we are going to deal it with unsteady state. So let's substitute. Now let's what to say? Open it up and differentiate CA j omega e raised to j omega t equal to rho square CA by rho x square e raised to j omega t. So you have I made a mistake. dA rho square CA by rho x square minus j omega CA. So this is of the form y equal to mx square form. So you know how to solve such differential equation, which you're going to do now. First, we have to take dA to the other term because that's the formula form we need that to be there. And m is equal to be square root of j omega by dA. So similarly, I hope this is clear. Now similarly for the product, we have Cb equal to C3 e to the power mx plus C4 e to the power minus mx, and m dash becomes j omega by dB. Now let's look into the boundary conditions we have to apply. Now let's look into what to say how the boundary layer condition. So we let's look into the boundary condition. Just give me a moment. Yeah. So let's look into the boundary condition. At x equal to 0, you have dA dou CA by dou x at x equal to 0 equal to IF by NF. So this equation we have used previously also. We already know CA is equal to CA due to the DC plus CA delta e raised to j omega t. We also know IF equal to IF DC plus IF AC, which I am writing as del IF, right? Now let's substitute this both in this equation and see how it will come. So it becomes e raised to j omega t. You know, CADC is a constant, so that will get cancelled. E raised to j omega t dA rho CA del by rho x at x equal to 0 equal to del IF by NF. Same way, IF AC is also not considered, or it becomes IF AC by NF. Now this can also be written as del IF e raised to j omega t by F. Right? Where IF del IF is equal to IF AC naught e raised to j omega phi. Now let's substitute this. You will get, where did that j omega phi come from? So this is a formula you have to use. Okay, dA dou CA so how did that come? Like IFAC, okay, this you wrote over here, right? IFAC is nothing but IFAC not e to the power j omega t plus phi. I'm just writing IFAC not e raised to j phi e raised to j omega t. This one is IF then e to the power j omega t. So this is how this equation is coming. Okay, this is, so now I'm continuing it. So now we also know at x equal to del, the surface concentration becomes equal to the bulk concentration. So these are the expressions we are going to use. So you know concentration are constant, right? Couldn't oscillate. Oscillation are fixed, or I can say it is zero. So this means CA del will be equal to 0. So now when we are applying the boundary condition, so I'm giving a gist of how to proceed with this, where we will take time. So when you are applying boundary conditions, you have CA del equal to A1 e to the power mx plus A2 e to the power minus mx. Now let's apply the boundary condition 2. Which is the boundary condition 2? This one. So you have at x equal to del. At x equal to the boundary line thickness, after that what happens is CA becomes CA bar, CB equals CB bar. Then you wouldn't see any oscillation. So CA del will be equal to 0. When you're substituting this over there, you'll get A1 as 0 and CA del equal to A2 e to the power minus mx. Now let's apply boundary condition 1. Where you see dou CA by dou x equal to A2 e to the power minus mx. Now solve. I mean, we have to substitute, find out. So how do you proceed with that? A to dA minus m e to the power minus x at x equal to 0 equal to if. So this is the equation which we are talking about, right? Now when we solve it or rearrange it, you will get if del f dA minus 1 by m. Once you substitute it back, you will get if del f dA minus 1 by root of j omega by dA into exponential of minus root of j omega by dA into x. This is the final expression you will get for CA del. Now I can simplify this further and write CA del equal to minus IF del F j omega dA exponential minus root of j omega by dA to x. This is the expression you're getting. Now let's find out what we have to find. What is that? One is del CA, one is del CA, which is CA dash e to the power j omega t. Del CA at x equal to 0, you will have CA del at x equal to 0 e to the power j omega t. Now let me substitute back what I got. This part minus if by f into root of j omega dA e to the power j omega t minus del if. This basically by combining if into e to the power minus j omega t, you will get delta if. J omega t. Now similarly, we'll do this even for CB. E to the power j omega t. Del if by f j omega dB. So this is how you will be deriving for delta CA and delta CB by considering the time variation also. Now finally, what is our aim? To find out the current and the impedance. Let's do that. Del if equal to F into B1 K1 DC CA at x equal to 0 minus B minus 1 K minus 1 DC CB at x equal to 0 EAC plus F K1 DC minus del IF by F into j omega dA plus K minus 1 DC del IF by F into root of j omega dB. This is your expression, right? Now let's simplify this fully. So you will get del IF equal to 1 plus K1 DC by root of j omega dA plus K minus 1 DC j omega dB equal to F into B1 K1 DC CA at x equal to 0 minus B minus 1 K minus 1 dc Cv at x equal to 0 into EAC. So you have delta IF by EAC, you will get the YF, or you can write it in terms of ZF. Rearrange it, you will get this particular equation. So this is a expression for impedance when you consider the unsteady state. So probably we have two more derivation. One is for a finite boundary layer and the semi-infinite. So once we complete that, we'll be able to start the problem. So my aim for today will be to complete both of them and to start with the assignment questions. Okay. So let's move on to under semi-infinite condition. What's happening? This case, EDC can't be another value other than 0. Right. So EDC is going to be 0 for a semi-infinite boundary condition because semi-infinite boundary condition means it's not going to immediately meet the x-axis. It's just going to be a straight line, but after a very long time or at a very low frequency, it is going to be. So that happens when the electrode is stationary or not. Okay. So So del tends to infinity. So in this case, the boundary layer is going to be very infinitely thick. So we say it's infinite. And only if this happens, so equilibrium is possible only at del tends to infinity. So here you will have CA at any point x equal to CA naught plus CAB bulk minus CA naught to x by del. And when this tends to infinity, you have CA of x becomes equal to CA naught. So this will take infinite time to achieve or to have this condition to be reached, it will take infinite time. So in this case, we cannot take any other condition, boundary condition other than the equilibrium condition as we are saying that it keeps on moving. Okay. So we know what is the expression. Let's write that down first. K1 dc by root of j omega dc plus k minus 1 dc by root of j omega dB by f into b1 K1 DC CA at x equal to 0 minus B minus 1 K minus 1 DC CB at x equal to 0. So here the total impedance would be sum of charge transfer resistance plus the warburg of the reactant plus product, which will say the total warburg impedance. So, which is the constant coming, which is not dependent on the frequency. That I can say is the charge transfer resistance, and in this case, RT becomes 1 by F into B1 K1 DC CA at x equal to 0 minus B minus 1 K minus 1 DC CB at x equal to 0. Similarly, what is Z omega A or W warburg of A due to the reactant becomes K1 DC by from J omega dA by F into B1 K1 DC CA at x equal to 0 plus B minus 1 K minus 1 DC CB at x equal to 0. Similarly, Z omega B WB, so the warburg of the product, it becomes K minus 1 DC by root of J omega dB by F into B minus 1 K minus 1 DC CA at x equal to 0 minus B minus 1 K minus 1 DC CB at x equal to 0. This is a formula you get for everything. Here you will see the impedance of A and B. This dependent on which terms? It is dependent on K1 DC. Okay, and conservation also. So this means that it is dependent on kinetics. Okay. Now let's consider a special case. Let's consider a special case where UDC equal to 0, which means it's OCT. CA at the interface, it becomes equal to CA bulk. CMB concentration of the product at the interface, it also becomes equal to CB bulk. K1 DC equal to K1 0, K minus 1 DC equal to K minus 1 0, and forward and backward reaction, they are equal. So when I'm applying all of these conditions together in the equation for RT, or not RT but the entire ZF. So let's take the denominator of this. What is the denominator? F into B1 K1 DC CA at x equal to 0 minus B minus 1 K minus 1 DC CB at x equal to 0. Okay. If I am just consider, okay, let's ignore F. Faraday's constant, it's outside. If I now substitute for everything, and B1 is alpha and F by RT, N is 1. Then K1 DC is K1 0, CA at x equal to 0 is CA bulk minus 1 minus alpha minus or 1 minus alpha, that is B minus 1 RT. K minus 1 DC is K minus 1 0, CB at x equal to 0 is CB bulk. Now also at equilibrium, I know K1 0 CA bulk equal to K minus 1 0 CB bulk. So this means this term and this term are equal. I can take them out. Let's say K1 0 CA bulk and RT is also common. I'm going to take it out and write alpha F minus of minus plus 1 minus alpha so this and this goes and you have K1 0 CA bulk F by RT. So this is the denominator. Now substitute this back in the expression for RT. So because RT is 1 by the denominator. 1 by this value is RT. So what do you get? RT by, there is already one F outside, right? This F square, K10, CA bulk. This RT. Similarly, you can find out what is ZA, what is ZWB. So you will have K1 naught root of J omega dA at the top. So if I write this is K1 naught by root of J omega dA, and you will have K10 CA bulk F by RT. So you'll get RT by F into CA bulk root of J omega dA. The right properly it becomes RT by CA bulk F root of J omega dA. Same way this will become RT by CB bulk F root of J omega dB. So this is how you'll be getting the expression. These expressions are needed when you're solving the problems. Don't forget there was an F square because it is F into that denominator. So you need to have that. Now let's find out what is the total Warburg impedance. So this is the expression. So you have RT by F square CA bulk J omega dA plus RT by F square CB bulk into root of J omega dB. You can take out RT by F square. Okay. So how do I'm going to write this as something. Let me introduce a sigma, which is RT by F square 1 by root 2 of 1 by CAB root dA plus 1 by CBB root dB. If I substitute this in this one, RT goes, F square goes. So CAB into CAB, dA, CBB, dB. For that, I'm going to substitute together as sigma. So if I write ZW, it becomes sigma root 2 by root of J omega. This is the expression for total impedance of water. Now, I can further simplify it. How? I know J equal to E raised to. I can write it in terms of the imaginary part. Now let's write J to the power minus 1 by 2 as it is here. What is it? E to the power I 5 by 2 into minus 1 by 2, which is e to the power I 5 by 4, right? Which is cos 5 by 4 minus sin 5 by 4. What is cos 5 by 4? 1 by root 2 minus j. Sin 5 by 4 is 1 by 2. So you'll get 1 minus j root the whole by 2. Substitute this particular value back in this one. What do you get? Sigma 2 root j root omega. The sigma root 2 by root omega. And this is what? This is same as writing j to the power minus 1 by 2, and we have found out the value before. as 1 minus j. So sigma w, you can write in terms of waarburg like that. You write omega super subscript. This is the expression where sigma w is the semi-infinite waarburg. So, so this is the condition for semi-infinite boundary condition. Let me just complete the derivation, that will become easy to start the problems. Now let's go to the next one, which is simple electron transfer reaction, where I'm talking about finite boundary layer thickness. So where you have A1 giving B plus electron, you have K1 and K minus 1. So you have IF, which is equal to F into, formula remains same as before. Now, as we did before, we will be differentiating the current with terms of potential and the concentration CA, CD, because all of three are independent terms. I want to find out each terms. Okay, as we did before. So I'm not explaining much. I think you have understood this. In the start of the class, we have already done this. Same way, dou IF by dou CA is equal to K1 dC into F. So I am by rho Cp equal to minus K minus 1 dC into F. Now we have to find del Ca and del Cb. Del Ca equal to CAAC, which is CAAC naught e to the power j omega t phi equal to Ca del e to the power j omega t. Now substitute in the fixed law of equation. There is a general procedure you have to do. Substitute for Ca. So here it is a function of time, so we keep this term. Here is a function of x, so here e to the power j omega t goes out. So differentiating e raised to j omega t by time, you'll get j omega e raised to j omega t equal to dA e to the power j omega t dou square Ca by dou x square. J omega t goes out. Right? I hope all of you are able to follow this portion. If not, let me know in comments. So if I simplify, I'm going to now simplify this. So this is of the form y dash square minus mx. So I want to solve this. C dash equal to C1 e to the power mx plus C2 e to the power minus mx. Now at boundary condition at x equal to del, as told, there the concentration becomes equal to the concentration of the bulk and you won't have the oscillation of the C and del will be equal to 0. I'm gonna just rearrange it. Now I'm gonna find out what is the rate constants. I mean C1 and C2. Now at x equal to 0, dA rho Ca by rho x at x equal to 0 equal to If by Nm minus dB rho Cb by rho x at x equal to 0. Now let's simplify it and do it. What do you get? dA rho Ca AC by rho x. If I write in terms of If AC by F equal to del If by F. Now what is del IF? It's IAC naught e to the power j omega t plus phi by F. Now if I am just simplifying, it becomes IAC dash e to the power j omega t because IAC naught into e to the power j phi becomes equal to IAC del. We want to differentiate the above equation C1 m into e to the power mx minus e to the power 2m del minus m e to the power minus mx. Now we just have to simplify it. C1 m e to the power mx plus e to the power 2m del e to the power minus mx. Rho C by rho x at x equal to 0 equal to C1 m 1 plus e to the power 2m del. Now we want to substitute this back into the expression which says dA C1 m 1 plus e to the power 2m del equal to Im by f. Now let's rearrange to find out C1 and C2. You get C1 from here. C2 gets expressed in terms of C1, so you'll get C2 also. Now I can further simplify this as C1 equal to IS then F into this directly from the formula and same way C2 equal to minus IF del 2F to j omega dA super minus m del cos hm del. Substitute both in CA expression. Now let's rearrange it. Now del CA equal to CA del e to the power j omega t. Sorry for speeding this up because I'm curious to start the question answer solving session. So this kind of step by step I'm writing on everything. You can just look into it, and if you anyone get any doubt, you can ask me in the next class, or you can just ping me through the comment section. Then finally, delta CB at x equal to 0 equal to delta IF by into j omega dB tan HM delta. Finally, we're gonna write the expression for delta IF and the ZF. That's by substituting it back into the equation, you get this directly. Now, you have all those terms minus. Now, finally, when you are rearranging this, you'll get something like del IF equal to F into V1 K1 DC CA at x equal to 0 minus K minus 1 DC V minus 1 CB at x equal to 0 by 1 plus K1 DC tan HM del by root of j omega dA plus K minus 1 DC tan HM del root of j omega dB. Finally, you will get the Faraday impedance as ZF equal to 1 plus K1 DC tan HM del by root of j omega dA plus K minus 1 DC tan HM del dB by F into B1 K1 DC CA at x equal to 0 K minus 1 DC B minus 1 CB at x equal to 0. So here, as before, you have both RT term plus ZB omega warburg plus ZB warburg. So 1 by F into B1 K1 DC C at x equal to 0 minus K minus 1 DC B minus 1 CB at x equal to 0. That will be the RP value. So the second term corresponds to that of A impedance due to warburg, and the third term is because of the warburg impedance of B. So if there is rapid mass transfer happening, you can say that C and CB values are fixed. And in that case, when K1 DC will be increasing and K minus 1 DC will be decreasing, you'll be seeing that RP is decreasing. Just give me a moment. Yeah. Now, let's move on to the question answers. Okay. Let me take the questions. So we want to discuss the assignment. So this is assignment number 8. Okay. So the question one, in case of rotating this electrode, as per Levitt's equation, the diffusion layer thickness varies as dash of rotational speed. So its options are square root, is it square, inverse of square root, inverse of square. So how does it vary in the rotating disk electrode? As per the Levich equation, the diffusion layer thickness, which is there, it is varying as inverse to the square root of omega, right? There is the equation. So let's start here. So we saw here del equal to 1.61 d0 to the power 1 by 3 omega to the power minus 1 by 2 and gamma to the power 1 by 6. So it is inverse. Minus means it's coming inverse to the power 1 by 2. So the answer is inverse of square root. This is the correct answer. So now the next question. Given the diffusivity of a species, ten to the power minus 5 centimeter square per second, kinematic viscosity is 10 to the power minus 2 centimeter square per second. Estimate the diffusion layer thickness when rotational speed to 25 rpm. Then equal to how much? Given the diffusivity of species to be peak values given as 10 to the power minus 5 centimeter square, kinematic viscosity, which is to the power of 1 by 6, it's given at 10 to the power minus 2. You have to estimate what is the diffusion length is delta and rotation speed is 25 rpm. So you see it is 1.61 to something. So 1.61 accounts for few of the conversions. So you have to make sure that they are in those particular units. In this question, diffusivity coefficient, diffusion coefficient is 10 to the power minus 5 centimeter square per second, which is okay. Gamma is 10 to the power minus 2 centimeter square per second. That's also okay. Omega equal to 225 RPM, which is 225 into 2 pi by 60. So let's calculate what the value is. Yeah. So this value you should be getting as 23.57 radian per second. So omega shouldn't be in RPM, we have to express it in radians per second. Now you know the delta boundary line thickness formula is 1.61, diffusivity raised to 1 by 3, omega raised to minus 1 by 2, and the viscosity, kinematic viscosity to the power 1 by 6. Let's find out this value after substituting everything. So, what is the answer you're getting? I'm getting it as 33.16 micrometer. So, this is the answer I'm getting when I'm solving. Now, let's look into the next question. Given the diffusivity of a species is 10 to the power minus 5 centimeters square per second, kinematic viscosity is 10 to the power minus 2 centimeters square per second, estimate diffusion layer thickness when rotation speed 1600 RPM, gamma equal to how much micron? Same as the previous question, except that you see here the omega value rotation speed is increased, and same way you have to convert it from radians to radians per second from RPM. Let's do it. Omega is given as 1600 RPM, 1600 to 560. You have to find out the value. Please use the calculator, do it by yourself, and then cross check the answer. So I'm getting 167.47 as the radian per second. Now substitute everything in delta equation 1.61 d to the power 1 by 3, omega tends to minus 1 by 2, and gamma tends to 1 by 6. Raised to, not anything. Solve it and find the answer. And solving, I'm getting 12.43 micrometer. So when compared to the previous question, your the thickness value is reducing. Why reducing? Because your RPM is increasing from 225, it has increased to 1600 RPM. And you know, omega, it's inversely proportional to the, sorry, I'll write this one minute. Your boundary layer thickness is inversely proportional to the square root of the RPM. So when your RPM is increasing, you see that the boundary layer thickness is reducing. So in reality, when you're giving some sort of rotation, the molecules, the reactant molecules can diffuse closer to the electrode-electrolyte interface and the reaction is happening. In the same way the product which is formed can diffuse out of the electrode-electrolyte interface because of the rotation. In that way, the free surface is easily available and the reactants easily move towards it, products easily move out. So the reaction is sustained. So that's why when you are increasing the rotation, you see that the boundary layer thickness is reducing. The boundary layer thickness is that region where you see a concentration gradient or there is a limitation in the availability of the reactant there. So that's what it means. We'll see one last question, and that being for a simple electron transfer reaction, you have a simple electron transfer reaction. The coupling of mass transfer and the electrode and the kinetics at the electrode surface is described by with options relating the species flux to the current. Option B, equating the species concentration with bulk concentration with second law. Option D, none of the above. So the question is that the electrode interface, how you are relating the mass transfer and the kinetics. So kinetics means the reaction happening. So in normal way, how do we do it? There is no mass transfer. First, we'll find out the steady state fractional size it's occupied, and after that, we'll find out the current. Then we'll substitute. We'll write IF by EAC. So when it comes to kinetics, the terms which are involved are current and potential. And when it comes to the mass transfer happens when the reactants are not readily available or the products cannot diffuse out from the surface or not. There's a concentration gradient. So the concentration gradient is given by the which equation? The Fick's law. So what does that say? This equation. So in multiple classes, we saw this is that equation. Yes. So here the concentration gradient, that is the diffusion coefficient into the concentration gradient, it is dependent upon the rate of the reaction, which is forward reaction minus backward reaction, which is equal to IFN by NF. So at any surface, this flux, okay, second law of diffusion, this happens when it's dependent on the time. But otherwise, the concentration gradient that occurs which is B into dou CA by dou X. It is dependent upon the rate of forward minus rate of backward direction, which we can express as which one? IF by NF. So here you are relating current and also with the species flux or the change in the concentration of the species. That's a concentration gradient. So this corresponds to option A, which is relating the species flux to current. So now for the next class, we'll be dealing with any questions. We'll be solving questions. It's going to be a little lengthy. Even next assignment and all, we'll be winding up by the next class. And after that, we have a formal revision also in the last class where I'll be summarizing whatever we have seen. Okay, so this is all for today. Now we'll meet in the next class. Thank you.